Good morning, everybody, and thank you for attending today's webinar. My name is Matthew Byer, and I'm in technical sales here at Thermtest. Today's topic is on homogeneous and heterogeneous materials tested via transient and steady-state methods prepared by Dale Hume. Just to note, if you have any questions during the presentation, you can place them in the chat box in the bottom right, and we will have a Q&A period where all questions will be answered by Dale at the end. Without further ado, I'll hand it off to Dale.
Thanks, Matt. Welcome everybody to this chat. This webinar came to us by almost a second part to our webinar entitled 3 Thermal Conductivity Methods Compared, GHFM, TPS, and LFA on Anisotropic Graphite Composites, which you can find on our website. And that really focused on nano-type composites or graphite-type composites, where when you have material characteristics and heterogeneity affecting error from the ideal theory on methods. And so what we've done with this is look at the other scales. So when the materials aren't nanoscale, larger components and particles, what are the effects on the ideal theory? So let's proceed. So the agenda will be a short discussion on thermal resistance and thermal conductivity, effective or apparent thermal conductivity. Who cares about this property? Methods for solids, TPS and MTPS. Transient state, we'll look at the guarded heat flow meter as the typical steady state method for measuring more conductive materials as compared to heat flow meter for insulative type materials. So I'm sorry about the spelling on applications. The materials we've basically designed and come up with in our printing, we've introduced components to create some different types of composites to demonstrate error in testing and its effect on ideal theory. And then ultimately, what is the question is, what is homogeneous enough when you're looking at using different methods? So what is thermal resistance and thermal conductivity? Thermal resistance is a ratio of temperature difference between two phases of a material, basically across the thickness, the resistance of unit flow per unit area. The higher the thermal resistance, the lower the heat transfer, or the more insulative. The lower the thermal resistance, the higher the heat transfer, or higher heat transfer. This is most appropriate for characterizing heterogeneous materials when other modes or some degree of heterogeneity is present. It is uniquely designed for that approach to materials. Thermal conductivity, this is an intrinsic ability for a material to conduct heat. It is one of the three methods of heat transfer, other two being convection and radiation. The higher the thermal conductivity, the higher the heat transfer. The lower the thermal conductivity, the lower the heat transfer. There are some assumptions made on the methods used that measure conductivity directly that one should consider when selecting a particular method to use on your material. So who cares about thermal conductivity? Of course, academia for research and general characterization of materials, R&D, develop materials to increase or decrease the rate of heat transfer for specific applications. Quality control, so this would be continuous measurements on materials to have a pass or fail parameter of quality. Optimization, so selection of materials for a particular application. Specifications, so that would be measurements to market a material or for sourcing. Ultimately, many of these measurements that are produced by thermal conductivity methods end up in simulations. We see that as a relatively critical use of this data. Thermal simulations often are done in steady state, one-dimensional analysis on a constant load on a model to determine temperatures at junctions, heat flow rates, and heat fluxes. Of course, additional transient analysis can be performed to determine initial conditions or power on conditions, if you will. Measurement errors from thermal resistance or thermal conductivity are, of course, transferred through to the simulations and can create uncertainty in those simulations. Some of those errors are if you are doing a one-dimensional simulation and your data is actually not one-dimensional, meaning you've measured an average for a anisotropic sample or have error in your data, and these errors will affect the quality and certainty of your simulations. So the two groups of most popular groups of methods for solids are in the transient spectrum are transient plane source type sensors. So whether they are a disk or a modified version of the disk, their timescales are transient. So typically 1 to 80 seconds. Small sample size, again on a scale of 10 millimeters to an inch or an inch and a half. And the assumptions from the theory are that 100% of the heat introduced from the sensor diffuses in the material through conduction. There's a stringent shape of penetration based off calculation models. That would be three-dimensional. So if your material is isotropic and truly homogeneous, the heat would diffuse in all directions at the same rate. One-dimensional, so this would be a specific approach to a material where your material dimensions fit the diameter of that material in your samples tall or elongated. Again, the assumptions made that it is isotropic and highly organized. So if there is any anisotropy, that the anisotropy is highly organized. Again, because there's no error. Rather, there's no calibration for the error when you don't meet that theory assumption. Anisotropic, so this would be ability to measure two planes of a material. The theory for the anisotropic testing by transient plane source methods is that your anisotropy is highly organized. And what I mean by that specifically is that if you have particles, that those are aligned in a manner that through the thickness, the radial thermal conductivity is maintained at the same measurement data. Difference in time scale or difference in measurements of time, which give you different thermal anisotropy values, are going to create error in your results. So a little bit more detail on that. Measurement considerations for transient plane source or modified versions of it. If it is not highly organized, rather, if your material is highly organized, various transient methods can be considered. If the thermal conductivity of the fillers and particles are close to that of the matrix, this effective shunting is minimal. So through various webinars and research papers, we see that the smaller the particle, the more well dispersed it is, that sensitivity to the heterogeneity is reduced. Of course, the thermal conductivity can increase with the introduction of those particles, but the larger they are and the higher the thermal conductivity, the more sensitive you are to the heterogeneity or poor distribution of those particles. What effect does that have on the use of a transient method is, again, the assumptions that if you are measuring an isotropic sample or you are measuring an anisotropic sample, each having their own calculation model, that they are well organized, those particles are well organized. And if they're not, you get some thermal shunting, which would be small internal temperature gradients across those particles. So during these transients, which are again in the seconds or tens of seconds, this sensitivity to this shunting can overestimate the thermal conductivity and cause distortion. There is no calibration or correction for this phenomenon, at least not yet. Your sensor that you're using knows nothing about your material other than its physical dimensions. And if you're doing anisotropic, it does know the input requirement is volumetric specific heat, but it does not know anything further about your material. So therefore, for accurate results with these two approaches, one being isotropic or bulk, second being anisotropic, there are some very tight assumptions that you have to know about your material to ensure you're getting accurate results. If the layering is repeating, so a layer, anisotropy could come in other forms, such as a layer. If the layer is repeating and individual layers are not too different in thermal conductivity from each other, again, transient methods could be satisfactory. Layers should not be too thick or too different from the matrix that they're in. With a high degree of anisotropy, directional heat loss is not well defined. So again, that heat diffusing in a manner that is not covered by the theory of your testing method can cause error. Due to the complex nature of layered materials, it is difficult to confirm that the full thickness um, is included in the result. Often the penetration depths introduced from calculations from raw data are based off the thermal diffusivity measured by that same instrument. So if there's error in the diffusivity results caused by introduced error from not meeting the ideal theory assumptions, your penetration depth diffusivity would be wrong. Therefore, it's really difficult to ultimately know that you're sampling the whole sample. Steady state, the guarded heat flow meter ensures that interlateral heat loss is eliminated and that the full thickness and one-dimensional thermal resistance is measured and one-dimensional thermal conductivity is calculated. There's anything between those two plates, upper plate and bottom plate, that is brought together or clamped around your sample is part of the resistance measurement. So in the time scales for steady state are into the tens of minutes, let's say 30 or 40 minutes. So all temperature gradients caused by resistances or heterogeneity are part of the resistance measurements, and those are mature. So you have a real measurement or true thermal conductivity measured. A little bit about the scale of samples for a guarded heat flow meter is longer test times, as I mentioned, 30 to 40 minutes. Larger sample sizes, again, different from heat flow meter for insulation materials. Guarded heat flow meter has typically a defined diameter of 50 millimeters to 50.8 or 2 inches diameter and up to 1 inch or 25 millimeters thick. This method would measure the heat flux across a defined sample thickness, measured by the instrument itself. Precision on the measured thickness ensures accurate thermal resistance calculation. And then again, from that measured resistance, a calculated thermal conductivity is usually part of the software and/or math of the method. It is ideal, of course, it can be used on homogeneous materials, but it is ideally suited for heterogeneous materials or disorganization of anisotropy, which is ultimately a heterogeneous material. Your values represent a one-dimensional heat flow, and that is achieved through active guarding. So you have your sample sitting between two plates, and different than the heat flow meter, which uses passive guarding. A guarded heat flow meter actually uses an oven that surrounds the sample, and that is set to the same mean temperature that is created by the delta of your plates. So any mechanisms of heat transfer that are between those two plates and part of that resistance are allowed to become steady state, and they become part of that thermal resistance measurement. So how does anisotropy affect use of a guarded heat flow meter? If the particles introduced are disorganized or non-repeating, whether it's layers or particles, the measurement of resistance is recommended. This method is ideally suited for that, such that any lateral heat loss is eliminated and that there is a one-dimensional temperature gradient created across your sample. If fillers are significantly different in thermal conductivity compared to the matrix, the thermal shunting is negligible. Again, with thermal resistance, you are looking at mature effects like this. Typically, again, 30 minutes to achieve steady state conditions. These temperature gradients are mature and do not have an error effect on the resistance. It is well published that the disorganization or particles that are disorganized or not well defined and organized will have error on transient. And when you compare them to steady state, there would be poor correlation. If you compare truly homogeneous materials, such as parts, glass, you get the same number on steady state and transient. It's when you diverge from the assumptions made on transient that you get the bias we see. A few examples that we offer on guarded heat flow meter is our new GHFM-01. This is a laboratory instrument. I won't go into every detail on this, but it has advanced controls for temperature, applied pressure, and thickness sensing. This is a computer-controlled device which can test up to 300 degrees. And then we have a more economical version of that with limited capabilities, but ultimately measures resistance in a similar way on a similar sample size. So again, in this case, the sample size is 2 inches diameter. and that allows us to have chamber, rather two plates that come together in a guard furnace that limits the effects of lateral heat loss. So that's why we have that defined size. And again, the thickness can vary up to 1 inch. So here's some polymers that we 3D printed to demonstrate on a larger scale of particles or introduce heterogeneity, what the effects are on steady state versus transient. So we, as a control or a base sample, we 3D printed using a PETG, which is a glycol modified filament. We 3D printed 50 or 2-inch diameter by 14.5 millimeters thick. And we did, as you're going to see with many of the webinars when we're comparing transient and steady state, we do different time scales on transient because that is the typical approach to ultimately measuring the best you can with a transient on a heterogeneous materials is to look at longer test times to measure as much of the material as possible. And that has merit, and it does improve your results, but ultimately you have introduced error that is not defined because of that. Again, when your time scales change, your thermal conductivity, you have now error introduced to your ideal theory. And the larger the change in time scales and thermal conductivity, the greater degree of error. So here, this material is homogeneous on a scale of between 10 and 80 seconds. The results change very little. We measured that same sample with GHFM, which is on a time scale of about 30 minutes, and resistance-based thermal conductivity was indeed higher. Again, the through thickness GHM result is guarded against lateral heat loss. We believe that this difference in thermal conductivity is the difference of bulk TPS result compared to a through thickness value by GHFM, and this is caused by the possibility of anisotropy caused by the printing process. There could be some bias in other ways, but I believe that to be, based off other experience as well, I believe that to be the major difference between these two results. So what we did with that same matrix, we 3D printed a pocket to allow a stainless steel plate to be inserted, and those two halves were brought back together to create a sample of similar dimension to just the control. So that plate was about 38 millimeters in diameter by 3 millimeters thick, which stainless steel has about approximate conductivity of 13.5 watts per Kelvin. And as you can see, this was a very interesting finding, kind of a surprise, that on time scales between 10 and 80 seconds, the thermal conductivity didn't change at all. And we believe we did see some effects of reflection at longer time scale in the sensitivity residual, but ultimately, because the matrix is of a low conductivity, a low thermal conductivity, the effects of reflection and the effects of the plate weren't seen. Essentially, we weren't able to see we weren't sensitive, rather, by this method to the heterogeneity caused by the stainless steel plate. We did longer test times of 160 seconds and 320 seconds, and we were starting to hit the edges of the material in another direction. Again, we're measuring bulk, but you can see that in this case, our results hadn't changed. So we're basically not sensitive to that. The thermal conductivity through the thickness by GHFM, there was an increase, of course, a small increase due to the series of resistance when you introduce stainless steel that would decrease the thermal resistance and increase the thermal conductivity. And then the next sample we did was the same dimensions of 3D printed, but we introduced some aluminum wire. And this was a 3D printing process where we stopped with 3D printed channels and introduced the wire and continued the 3D printing process until we achieved the full thickness. And it did the same time scales by transient. And you can see that more or less there was an increase in conductivity from the control, but the time scales show a sort of a lack of sensitivity to the heterogeneity caused by the introduced wire. We believe the increase of TP as a result is due to the alignment of the aluminum wire, which has a conductivity of around 170 watts per Kelvin. And this creates some anisotropy, which would have caused some diffusion along the length of those wires. But ultimately, the GHFM actually measured very little change in conductivity, again, as it is guarded against lateral heat loss, and you're looking at the full resistance across that thickness. Ultimately, those wires aren't touching each other in the through thickness direction, and they add very little to the increase in thermal conductivity or the decrease in thermal resistance when measured in a controlled manner. So the minimal change in the GHFM result is due to the thermal conductivity being through the thickness when compared to the bulk. So that bulk result would be not guarded, of course, and you would see some effects of that heat of diffusion through the wires. And then lastly, this is again a significant. We wanted to create a significant introduced particle just to show on the other scale of heterogeneity to add to the value of conversation we're having around these topics. So we introduced brass lugs that were 6 millimeter diameter by 10 millimeters thick, 19 of them in fact, into again the same 3D printed dimension with introduced pockets for each of those lugs. Brass having a conductivity of around 100 watts per Kelvin. And you can see from the time scales of 10 to 80 seconds that of course there is a dramatic increase in thermal conductivity from the previous two examples. These being much larger particles, you're going to see that. But the change in conductivity with time scale again is as we would expect, has an effect on the result, and in this case, much more dramatic effect because of the directions of heat pass available to the transient. Through thickness, we have again a large increase in the through thickness guarded direction by the guarded heat flow meter. So this would be a decrease in thermal resistance and increase in thermal conductivity. And the transient times do show a sensitivity to the heterogeneity caused by the brass lugs, which is what we would expect with such a significant introduced particle. The significant change in the resistance value from the GHFM is again thermal conductivity result of through thickness versus bulk. From the previous webinars on anisotropy, we knew these were not a good fit for anisotropic testing by transient methods because they're not well organized. So this was really an example of where does that effective heterogeneity ultimately take us? And you can see the value in guarded one-directional heat flow by GHFM. So ultimately, our findings from this, again, this builds off of a previous webinar entitled Methods Compared on Anisotropic Graphite Composites, which I invite anyone to listen to on our webinar. But we introduced larger scale heterogeneity from this webinar to demonstrate the importance of the assumptions made by transient theory. Transients, it's true, are easy to use, or perception of easy to use. They have rather complex math and calculation models with them. They're fast, but that comes with satisfying assumptions or knowing your material and the effects of air. So this webinar demonstrates that, of course, these are, as we expected, these samples are not ideal for anisotropic testing by transient methods due to the disorganization of the distribution of added particles or components. Sensitivity to heterogeneity can be reduced with low conductivity matrix in poorly dispersed particles. That was a little bit of an aha moment to see that depending on the thermal conductivity of your matrix and what you're introducing to them, if it's too far away from one of the surfaces, you might not see it all. And you might not even see the effects of reflection from that higher conductivity particle in your residual when you're looking at your transient residual, just due to the lower conductivity matrix not diffusing that back to the residual. Lack of sensitivity to heterogeneity, similar between bulk and anisotropic testing with low conductivity matrix and poorly dispersed particles, in the sense that you use the same sensor on a transient method, you use the same time scales, only thing different is the calculation model. So in fact, if we were measuring bulk or anisotropic, you would see similar, although the result might be an average or incorrect average, you would see similar scales of the thermal conductivity staying the same. So there's going to be an effect on sensitivity to time scales based off the raw data. If different time scales, so the ultimate question is, how do we know if our material is homogeneous enough to use a transient method? And a good way to compare or consider would be if different time scales show variations in thermal conductivity, you have introduced error in your calculation model for transient methods. What is the magnitude of that error? That is a very complex question, and it really comes down to the trends we're seeing is the larger the particle, the higher the thermal conductivity of your matrix introduced to your matrix, the higher the potential, especially if those are not well organized and well dispersed. Steady state guarded heat flow meter ensures any lateral heat loss is reduced and eliminated, and that the full thickness is represented in a one-dimensional thermal resistance. So between these two series of webinars and others, we've really touched on layer structures, small particle composites that are anisotropic, well dispersed and not well dispersed, organized and not organized. And there is a very specific need to use resistance-based methods depending on your material type, how again, and how well the material characteristics, whether it's isotropic or anisotropic or homogeneity or heterogeneity, how those are going to impact the use of a method. Certainly, there is a way to approach the use of transient methods with most materials, and we recommend that. It's just what we want to see is when the use of apparent or effective value to cover that error is used, that there's a well-defined description of what that error is. That's a rather critical importance to transferring the knowledge in the lab that there's an error introduced to the ideal theory, and that error gets transferred through to those using that data for simulations. That has an impact. And that's the end of our presentation. So I guess we have time for some questions and answers. Thank you, everybody, for listening in. One question I had was, what were the delta temperatures across the guarded heat flow meter sample? We had a mean of 25 degrees and a 20-degree delta. So that temperature gradient was created by the delta between top and bottom plate, being 10 degrees above and 10 degrees below the mean temperature of 25 degrees. That allowed us to compare a mean temperature on steady state to room temperature on transient. If there's no other questions, of course, you can always reach out to us by email or by phone. We can answer any questions you might have. Other than that, thank you for your time, and we'll see you in the next webinar.